So today we're going to be talking about how prosodic prominence influences fricative spectra in English. To start off with, it's useful to think about this question first in terms of where the autosegmental tradition that many of us work in starts off from. So in the autosegmental approach to tone and intonation, phonological tone specifications are representationally distinct from the segments that host them. What this means, of course, is that high and low tones and so forth are off on their own tier in the representation. And they really, to a large extent, only interact with segmental structures to the extent that well-formed mappings between those two levels of representation are negotiated. And this separation, the segregation of tone onto its own tier, has paid off in lots of ways for us in terms of how we understand the grammars of these systems. So just one example, if you look at the nominal tone in Mende, this is Will Laban's famous analysis from 1973, we can say that even though we've got on this slide a monosyllable, a disyllable, and a trisyllable, where in the first case, rice, we've got a rising tone on one syllable. In the case of cotton, we've got a low on one syllable and a high on the next. In the case of sling, we've got a low on the first syllable and then a high plateau across the two next syllables. Those are very different things from the point of view of the F0 contour in the signal. But at the level of phonological representation of tone, we're able to say ultimately those are in some sense the same thing. And obviously that's a kind of insight that just looking at the contour itself doesn't necessarily get us. Now, at the same time, there's been an increasing appreciation of the extent to which, at least in phonetics, at least in phonetic implementation, non-F0 factors play a role in the production and perception of what otherwise we think of as purely F0 targets. A couple of the things that we've been thinking about recently, one phonetic effect that seems to have consequences for the way some of those negotiations between tones and their segmental hosts are played out has to do with the sonority of host segments. So we know that the perception of F0 is more robust on higher sonority segments than on lower. And it seems that at least many tone systems avoid linking tonal targets to lower sonority hosts. We also know that in regions where major features of the spectral envelope change, so in areas with spectral instability, particularly around consonant vowel boundaries between the onset and the nucleus of a syllable, we know from David House's work that this compromises in different ways the continuity of F0 perception, such that we end up with a kind of perceptual chunking of what otherwise is a continuous F0 signal into discrete chunks associated with something like the sonorous rhymes of syllables, regions with more spectral stability. Now, in thinking in terms of this continuity or lack thereof, voiceless segments create an obvious sort of discontinuity in the signal, and that those are regions where there is no F0 at all. You know, for voiceless stops, you might imagine, at least in principle, and it's been suggested in the literature that that missing F0 might somehow be interpolated across the voiceless interval or restored perceptually or something like that. Recent work, both by our group and by Oliver Niebuhr and some of his colleagues, have shown that actually that's probably not true. In the case of voiceless stops, where you've really just got silence in an interval, the consequence of that for tone perception seems to be nothing. Effectively, that voiceless interval seems to be ignored. Now, in the case of obstruents, voiceless obstruents that are associated with high intensity noise during or immediately after their closure. So in particular, I'm thinking of fricatives. Here, there's a more complex story, and this is what we're talking about in this paper today. Investigating the consequences of different tonal environments for the realization of fricatives has turned up some interesting results. And in particular, this is this is the work of primarily Oliver Niebuhr, but a number of other research teams have found similar results as well. What they found is a correlation between local F0 levels on the one hand and the balance of energy in fricative spectra on the other. Such that in high F0 contexts, so in particular where this has been found in a bunch of different languages, German and I think Polish and some others, in phrase final position with rising intonation contours, fricatives like s or sh turn up with a higher spectral center of gravity than they do in lower F0 contexts. So for example, again, phrase final position in a falling intonation contour. Now this phenomenon, which Niebuhr has called segmental intonation, it's also been demonstrated that listeners are sensitive to these spectral differences. And it's been hypothesized that maybe what segmental intonation is about is actually speakers actively manipulating the locations of the energy peaks in fricative spectra in order effectively to mirror the local F0 targets that otherwise are getting effaced in this interrupted portion of the F0 contour. So if that were true, we could imagine that what we've got is a kind of perceptual integration between fricative noise on the one hand and F0 on the other, and that this integration might enhance phonological tone contrasts that are otherwise potentially imperiled by the voicelessness in certain regions of the signal. There is another possibility, though. This is something that's occurred to us and we've been interested in investigating. A number of the studies of segmental intonation, we listed one here, but a number of them have found this, note not just a correlation between higher fricative spectral center of gravity and higher local F0 levels, but also higher intensity of the same fricatives. Now that correlation with intensity is important because in the literature on the acoustics of fricatives, it's known that increased, what's usually referred to as vocal effort, effectively raised subglottal pressure, increasing airflow through the fricative constriction, yields both not just more intense frication noise, but it also enhances the higher frequency energy in the fricative spectrum such that you end up with a higher spectral center of gravity, if that's the measure that you're taking of the distribution of energy in the spectrum. So why is this important for the point of view of segmental intonation? Well, so first let me just show you what this might look like. These are, you're looking on this slide at two effectively S's pronounced by a speaker. In fact, this is a 10-year-old female native speaker of American English pronouncing, here on the left, you can see an imitation of what was described to her as a normal snake. Now here on the right is an imitation of what was described to her as an excited snake. This is what these different snakes sound like. Normal. Excited. You can see that snake was quite excited. And what you can see here in the spectrogram, well, you can see both in the waveform and the spectrogram, obviously there's higher intensity for the excited snake than for the normal snake. And while for the normal snake, you can see, the higher energy concentration we associate with an S, you can see a bit of a peak right here around 7,500 hertz. And that's where the most energy seems to be clustered in the spectrum for that normal snake. The excited snake, on the other hand, has loads of energy concentrated, much higher than that 7,500 hertz, right? And consequently, is going to have a higher spectral center of gravity as well, right? So in this case, the thing that some people have referred to as fricative pitch, or sibilant pitch in this instance, pitch obviously in air quotes that you can't see because I'm not recording, I'm not videoing myself, that excited snake is going to have higher sounding sibilant pitch than the normal snake. Just if you were curious, that was a 10-year-old. If you ask a 7-year-old to do the same thing, you get much less helpful results. The snakes don't know how to scream. Okay, so be that as it may, we might then ask, all right, well, if raising subglottal pressure, effectively raising vocal effort, results in higher spectral centers of gravity. Where do we find this happening in speech? Well, one place, obviously, where we find higher intensity in general in the signal, this has been associated with pitch-accented syllables in intonation languages like English or German. And this we expect to be the case in those syllables, whether they're bearing low tone specifications or high tone specifications, right? Accentedness is independent of tone specifications that might come to be associated with accented syllables. But we also find this kind of raised subglottal pressure. Subglottal pressure raising is one of the two commonly cited mechanisms for raising F0 in general, whether that's done because of a prominence or not. And so one other place that we find higher intensities and raised subglottal pressure is in regions where F0 is higher for other reasons. So for example, around boundary sequences. This is two sentences. One is a command with a high pitch accent and a low boundary sequence. On the left, it sounds like, give me CD again. On the right, you're looking at a question with a low pitch accent and a high boundary sequence. So this sounds like, give me CD again. And what you may notice, for those metrically identical weak final syllables, the last syllable in particular, in again, so the gen, I think what's fairly clear from the spectrogram is that in the L minus L% sequence on the left in the command, we've got lower F0 and really low intensity. It fades out in that last syllable. Whereas in the question, where we've got higher F0, we've also got much higher intensity, and that's really clear in the spectrogram of that last syllable. Now you could imagine if that has subglottal pressure raising, if that raised F0 is causing subglottal pressure to be raised, we might expect, were a fricative to be realized in that same final position, we might expect that it would have the same kind of higher airflow that would yield both higher intensity and consequently higher spectral center of gravity. And we wonder if that is effectively what's happening in some of the results in languages like German. So the hypothesis then would be that higher fricative spectral balance might in fact be a cue to increased vocal effort rather than to raised local F0 levels. And sometimes, of course, increased vocal effort is going to be correlated with higher F0, as in a syllable bearing a high pitch accent or around raised F0 in the final syllable of a rising intonation pattern. But of course, that won't always be the case, right? In a low pitch accented syllable, we might expect to see greater vocal effort, but lowered F0. So we wanted to test this. The way we did it, we conducted a production experiment investigating the acoustics of English S in a bunch of different prosodic contexts. So what we manipulated independently were, for the target syllables, the lexical stress status. So is it in a lexically stressed syllable? Is it in a syllable that's after the stressed syllable? Or is it in a syllable 2 syllables after the stressed syllable? So a posttonic or the distant posttonic syllable, second posttonic syllable. We also manipulated phrasal prominence. Is the word containing the target syllable under contrastive focus? Or is it in a region that's de-accented after the focus? And then we manipulated also the intonation contour. So are the nearest tonal targets effectively highs or lows? To see first the phrasal prosodic contexts, we had 4 possible contexts. 2 kinds, so in all these sentences that you're looking at, the target word is soda, and the S that we care about is the initial S in soda. Okay, so we have 2 kinds of imperatives and 2 kinds of questions. The imperatives are all supposed to have an H star L minus L% intonation contour, so high pitch on the stressed syllable of the target word, and then a fall and a low plateau after it. The questions are supposed to have an L star, low pitch on the target syllable, followed by a high plateau and a final rise. Okay, so when the target word is focused, this is going to sound like, so the question ultimately in the experiment, we had participants read part B in each of these mini dialogues. So if part A was, should I say coffee again? Then the participant read, for the imperative in the focused condition, say soda again, not coffee. Now, for the post-focus condition, what we did was put contrastive focus on say. So should I write soda again? Say soda again, don't write it. Okay, that puts the target word in a different part of that same high, low, low contour. And we did the same for questions. So say soda again, not coffee, and say soda again, not write it. And again, now we've got a low, high, high instead of a high, low, low. And we're putting the target word in different portions of that contour, either under the pitch accent or after it. The lexical stress patterns, the target words that we chose represented 3 different lexical stress patterns. We did 3 different vowels too, so an E, an O, and an R, a syllabic R. The stress patterns, we have stress on the target syllable, so this would be seeker and seedy. We've got stress before the target syllable. In this case, the fricative in question is intervocalic there, loosey and greasy. And then we've got a distant post-tonic S in words, 3-syllable words rather than 2-syllable words like odyssey and fantasy. Okay, those are our lexical contexts. So that was 16 words, 4 different contexts. We had them repeated 3 times. It's 192 tokens per speaker. We recorded the usual suspects, 9 college-aged native speakers of American English. We segmented the recordings manually, and any items that were realized with anything other than the target prosody, we eliminated, which left us with 1,166 tokens for analysis. The way we analyzed these things, we identified all the fricatives. We high-pass filtered the signal to get rid of all the noise under 750 hertz. And then we measured the closure durations. We measured the spectral center of gravity for the middle 50% of the fricative. We measured the mean intensity of frication noise in that same area. And then we took measures of local F0 at 3 points, 20, 40, and 60 milliseconds before the onset of frication noise, and 20, 40, and 60 milliseconds after the offset of frication noise. The idea being we would know what the F0 contour was doing as it went into the fricative and as it came out of it. And then taking the mean of those 6 measures, it gives us an F0 value that we used as a proxy for what you could think of as the missing F0 at the fricative midpoint would have been. What F0 should have been doing if there were F0 at that time, basically the middle of the 6 values that we measured. Right, this is just a representation of the sentences that we already talked about again, so I don't know that we need to go over this, but there you can see some pitch tracks. The target word in all of these is seedy. This is what local F0 context looked like. This requires a little bit of unpacking, but basically each vertical stripe that you're looking at here contains 6 observations, and those are the 6 F0 measures that I just talked about. So if you look here in the first stripe under focused and imperative, and then this column that we're calling pre-stress. So this, again, this would be the word seedy when it's focused in a command. Say seedy again. And we've got 3 measures that are going to be to the left of the fricative and 3 measures that are to the right of the fricative. So in the case of this say seedy again context, what you can see is F0 is high-ish before and high-ish after the fricative in question. Okay, now let's go and compare that. So count over 1, 2, 3 vertical stripes here. And now we're in focused, question, and again pre-stress. So again, this is going to be seedy, but because it's a question, this is an L star, right? So this is going to be, say, seedy again. Here we can see the 3 measures, the 3 F0 measures before the fricative are higher than the 3 measures after it, right? Why? Because we're dipping down into a low pitch accent. So we've got higher measures in the case of the H star than we've got in the case of the L star. So some predictions thinking, now obviously I don't want to go through all of these different contexts. You can pause and have a look at them if you like. The predictions that we want to make, what's going to be important is if you think, Well, if fricative spectral balance follows F0, where might we expect to find higher spectral center of gravity? Well, one place would be in the fricatives in syllables bearing an H star. So in, say, soda again, we might expect to find that S, to the extent that it's in a higher F0 context, to end up with higher spectral center of gravity. But we would also expect to find higher spectral center of gravity in the post-nuclear plateau, the raised region in the L star H minus H% contour. So in the S of Odyssey, in something like, say, Odyssey again, those would be two contexts that we would expect to support higher fricative spectral center of gravity. Lower center of gravity, we might expect to find, say, in, say, soda again. So in a fricative in a syllable bearing an L star. As we just saw, the local F0s are lower there. So we might expect lower spectral center of gravity. And similarly, we might expect those same lower centers of gravity in the post-nuclear trough of imperatives. So the S in Odyssey in a sentence like, say, Odyssey again, right? So just circling those, showing you those things again. This here on the left is the H star F0 context versus the L star F0 context. To the extent that the F0 mean in those circles is higher in the pre-stress, in the imperative, the H star context, than in the L star context, we would expect spectral center of gravity to follow that. And similarly, over here, we're looking at the boundary sequences. So L minus L% to the extent that measured F0 for all of our speakers is lower there on average, we would expect low spectral centers of gravity. And then up here in the circle on the right, to the extent that measured F0s are really high, we would expect higher spectral centers of gravity. Okay, so those are our predictions. What do we find? Well, basically not that. Here's circled, we've got, so this is spectral center of gravity for each of these different contexts. And circled, you've got on the left, the H star, the blue is the that syllable in words like CD and soda under focus. The red is when the focus is moved earlier. And then here on the right for the question, the blue again is under focus, the L star under focus, and then the red is when the focus, the L star is moved one word to the left. Okay, and what you can see is for that for the fricatives in the H star bearing or H star adjacent syllables and those that are L star bearing or L star adjacent, those centers of gravity are the same. The only difference that you see here, and actually notice this difference for all the blue-red pairs, notice that in each case, the blue one, that constitutes the fricative being in a word under focus is higher than the red one, which constitutes that same word, represents that same word with the fricative not under focus. That's the raising of spectral center of gravity that we were predicting under increased vocal effort. But having an H star versus an L star near you seems to do nothing to your spectral center of gravity. Okay, similarly, this is our L minus L% context versus our H minus H% context, right? So this is say Odyssey again versus, sorry, say Odyssey again versus say Odyssey again. And again, you can see the different tonal context has no effect on the spectral centers of gravity, right? Instead, we can see a couple things in this data. We can see each focused word has got a higher spectral center of gravity than its non-focused counterpart. And there does seem to be a little effect of lexical stress as well. This turned out to be statistically significant. So if you look for each sort of triplet, so 1, 2, 3 blues, or 1, 2, 3 reds, or 1, 2, 3 blues, or 1, 2, 3 reds, what you can see is the first member of the triplet, that would be the fricative in the lexically stressed syllable of the target word, ends up higher than any of the others for all the other conditions kept constant. That's interesting. It suggests that whatever additional effort is associated, or higher intensity is associated with being in the onset of a stressed syllable, is on average raising spectral center of gravity a little bit as well. Okay. If we plot, so on the left in this slide, we're looking at those same spectral center of gravity results. On the right, by contrast, we've got mean intensity for the fricatives plotted. Again, and this is in the same order. And what you can see is, wow, actually, intensity seems to capture the spectral center of gravity trends much better than local F0 did. In other words, these are broadly similar. Again, you can see the blue higher than red pattern across. You can see something like the lexical stress pattern that I was just talking about playing out here. And in fact, if you take a linear mixed effects regression model of this data, and you start with a base model that's just predicting center of gravity from adjacent vowel quality obviously changes spectral center of gravity for fricatives a lot because of co-articulation. If you add intensity to that model, you get a nice significant effect of the model improving from the addition of that predictor. If you add local F0, you don't get any such improvement, okay? Suggesting that some of the variability that we see in spectral center of gravity is directly related to intensity. So what do we get out of this? Well, things in this data that predicted significantly higher center of gravity for S include being in a focused word, right? So that's potentially our increased vocal effort. Being before the vowel of a lexically stressed syllable, again, potentially increased vocal effort, and having higher intensity, right? And that may itself be a consequence of that same increased vocal effort. Things that didn't seem to affect spectral center of gravity included either having higher measured F0 near you or being adjacent to a phonological high tone. What we want to conclude from this is that in American English, at least, and we think ultimately it may be the case that we can extend these results to other languages as well, higher spectral center of gravity for fricatives seems to occur in contexts associated with higher vocal effort. So we said lexically stressed or phrasally prominent syllables. Intensity measures show a pattern that's similar, and in all likelihood, both of these follow from the increased airflow through fricative constrictions that are caused by higher subglottal pressure in those contexts. Local F0 contexts, as far as we could tell, didn't influence fricative central of gravity at all. And so what we wonder is whether what has been called segmental intonation, in other words, changes in spectral center of gravity as a function of prosodic context, might in fact be a cue not to the tone contour, to the sequence of tones or the F0 contour, but instead to things like metrical prominence and speaker effort. And as we said before, it sometimes happens that those two things line up, but they don't always. And when they disassociate, as we saw in this study, it seems that the fricative centers of gravity follow the effort and prominence profile rather than the F0 profile. And that is it. Thank you.